Hello. In this lectures, we will look at these bending on prismatic beams, and we will discuss on this topic how we will solve this bending of prismatic beam, and also the frames using finite element analysis. So as introductions, we will look at this very brief about the beam. Beam is a structural element that primarily carries bending. So this is the main purpose of the beam, which is to carry bending, which is in the form of flexures or transverse loading. And beam also generally carries a vertical force, but they can also sustain a horizontal load due to, for example, earthquake, where we have horizontal movements to the left and the right, or to the front or back directions. And beam usually is different with other type of structure and can easily be recognized by its characteristics, which is its shapes, for example the cross sections, and the length, and the materials, and also the type of supports. Beam are used mainly in construction sectors. You may see this beam in constructions of a building, of stadium, which can easily be seen there. And they are typically made of steel, reinforced concrete, and sometimes based on wood. Depend on what type of applications and load that you want to support with this beam. So this is the typical beam structure that we can find in roof constructions, building constructions, and also the stadiums constructions, something like that. So as we can see here in the first top left figure, we can see this is where we have the beam, which is used to support the load that pressure, the body weight came from all the other small structure of this roof. Similar on these figures, on the top right figure here, where as we can see this is the main frame structure or beam structures that's used to support the load from the roof. And the top left figure here, on the other hand, showing the use of frames, the use of beams in the constructions of the stands or seat in the stadiums. So we have the beam here, beam there, and here is the beam as well, then here is the beam as well. So there are many beams were used here to support the weight of the supporters that's sitting on this stand in this stadium. And this is just another kind of construction which is showing that just another applications of the beam in the roof constructions. In this following figure showing the use of beam in other applications other than the building constructions. As we can see here, I put these examples where the beam is also used in other applications, such as in the shipbuilding. As we can see here, we have many beams were used in these ship constructions. And this is another example of the application of beam in the aircraft wing construction, which is, as we can see here, this is the wing, the beam which is used in the wing construction, and this is called here as a spar, but it's still a beams. And in the automotive construction, actually there are a lot of beam used in the automotive construction as well, and this is just one example of the beam that used for the support of the upper part of the car. Beam actually can be found in any shapes, and the most common type of beam which is in the I letter shape. So this is the example of the beam with the I letter shapes. On the other ways around, actually beams can also be found in any other shape which is in the form of C channels, hollow sections or O shapes, and the last one here we have the angles beam, and it's not necessarily to have 90-degree angle, so you may find the beam with different angles as well. And one of the most important characteristics or criteria of the parameter of the beam, which is its a moment of inertia. So in this table here shows the moment of inertia, how we can predict the moment of inertia for different shapes. So for example, if we take the first example here for a rectangle or parallelogram which has the length b and its height, which is given by d here, and if we consider the moment of inertia in the x directions by taking the x as our reference, so the moment of inertia in ix has, which is equal to b multiplied by the height to the power of 3 divided by 12. And if we view this structure here and calculate its moment of inertia by taking the y-axis as our reference, so the moment of inertia in y direction, which is equal to d multiplied by b cubes divided by 12. So similar applied to the hollow rectangular section, but we have to consider the hollow part in the equation as well. And this is the common I sections moment of inertia, where this equation can be used to obtain or to calculate the moment of inertia of the I sections both in x and y directions. So now let's talk about the general loading conditions, which is for our analysis purposes, which is in this case we still try to focus on how we can use the finite element method in solving the beam structural problems and the frame as well, which we will discuss it later. So there are three types of the common type of loading which is considered on a beam, which is the first one, which is known as the distributed load P, which is labeled by P here, and this distributed load is spanning from left to the right here with a certain length L. And the second load here, which is in the type of concentrated load, which is this kind of load applied at a point or arbitrary point along these structures or beam structures. And the last one here, which is known as the concentrated moment, which is in this case this moment applied also at arbitrary or known point, in this case point mk, and it carries the moment with k magnitude. So let's look at the deformations of the neutral axis. Due to the applied loads, the beam experiences an in-plane XY plane deformation, since we are working in X and Y direction, so the beam will experience the deformation in both X and Y directions. The deformation shape of the beam neutral axis is as shown in this figure here, where the deflections, deformations, transformations, and also the rotation shown in the positive deformations. So in this figure actually showing a beam structure which is under a certain load, and it's deformed to this shape. The dotted line here actually can be viewed as the beam at the rest, in the rest. So that means before we apply the load. So once we apply the load, then the beam will deform something like this. So if I travel or I sit at this point, the red point here, or at any arbitrary point along this beam, then I can experience here from the rest I am moving in the upward directions, so which is known as vertical deflections, and from the rest here to there, my body, maybe if I'm standing here, will experience some rotations, since as we can see here we have some slope. That means this particular point experience small rotations or slope depending on how much it bends. So the positive deformations or deflections is positive in the upward directions, and for the rotation is positive rotation or slope in anti-clockwise directions. So for the purpose of our finite elements, in this figure showing one beam structure which is spanning from left to the right, is then divided or chopped. We chop the structure here into four sections of four elements. Then for each element, it is connected between the nodes. So we have nodes number 1, nodes number 2, nodes number 3, nodes number 4, and nodes number 5. And it says here each node has 2 degrees of freedom. So that means here at one particular nodal point, we expect for the beam structure to have the deformations and also the rotation. If I am at this particular point, then I will have one deformation and one rotation. So that means here, if I consider element number 1 here, which is connected with nodes number 1 and nodes number 2, so for one element we have 4 degrees of freedom. Again here, for at one particular nodal point we have 2 degrees of freedom, which is in the form of deformation and rotation, but for one element we have 4 degrees of freedom, which is 2 deformations and 2 translations and 2 rotations. So to make these finite elements easy to be constructed and solved, so a positive sign conventions should be imposed. So the positive deformations for one beam elements, which is as shown in the bottom figure here. So the positive translation is always pointing outwards at any point, and also the rotation or slope is in the anti-clockwise directions. Since the beams involve bending, so the assumptions of linear variations in terms of the predictions of the translations or rotation between the two nodes along one element is no more accurate. So the Hermite shape function is suggested here. So we define the Hermite shape function so as to obtain the deformation at any point along a single beam element. So if I consider this is my beam element, which is spanning from node number 1 and node number 2 in the first top left figure here, then if we apply the Hermite shape function, then actually we can obtain 4 h values, which is h is given by hi equal to ai plus biz plus ciz square plus diz square. So if we look closely here, it looks like a polynomial equation where index high, which is referred to index from 1 until 4. So what is happening here? So if we look at H1, so at node number 1, which is reside on the left end of our element, where we have the natural coordinates which is equal to -1, where at this particular point for H1 the slope is equal to 0. That means there is no rotation. It is a flat horizontal positions of the beam at this position, but somehow in terms of the translation it has translations. At node number 2, where we have z equal to +1, then there will be no slope and no rotations. So this is what is the purpose of the shape functions. So between the 2 points, then the variation between in between the 2 points will look something like this. It is no more linear. So the 4 shape function actually can be expressed by the equation as shown in this slide. So for example, if we know the positions along our beam structure, where we want to calculate it all h value, then we can simply substitute the z into these equations. So by substituting this z in this 4h equation, then actually we can obtain the z, all the h value for all the z values here. For example, h1 actually refer to the translation, and h1 prime refer to the rotations or slope for the h value, and for the element that we consider where we take the z here equal to -1 and z equal to 1. Similarly, if we apply the similar approach, if we substitute z equal to 1 and z equal to negative 1 and 1 into H2 equation, then we can come up with this with this number, which is 0, which is referred to 0 translation at node on the left, and also 0 translations on the nodes on the right. However, we have rotation at the nodes on the left and 0 rotations at the nodes on the right. So this is actually can be represented by this curve here as well, which is there is no slope. We have slope but no translation, and we have no slope and no translations. So the deformation at any point or location within two nodal points can be obtained by this equation, which is actually this equation is interpolations equations based on Hermite shape function, where we had h1 v1 plus h2 multiply the derivative of v over z for the node number 1 plus h3 v2 plus h4 again multiplied by derivative of dv v over z at nodes number 2. So as we look closely in this equation here, in order to determine what is happening between the two nodal points, so we have to supply the calculated translations and rotation at nodes number 1, and also the translations and rotations at node number 2 in these equations. So what is dv over dz? So we need to replace the bracket terms. So the term in the bracket need to be replaced. So instead of we are working in the Cartesian coordinate system, but we have to actually much more easy to work in the natural coordinate system, dv over dz. So dv over dz is actually if we apply the change rule of differentiation, so dv over dz also equivalent to dv over dx times dx over dz. And but what is the x over dz? So from the natural coordinate systems equations, then we have the z and we have the x here. So if we divide the x, if we take the differentiations of the x over dz of this equation, then we get the L over 2. So if we substitute this dx over dz into this equation, then we can obtain that dv over dz equal to L, which is the length of elements we consider, divided by 2 multiplied by dv over dx. Alright, so once we substitute the v over dz by L over 2 dv over dx, then we obtain a new equation as shown on the top of this slide. And these equations can be written in a more compact metric form, which is given by v equal to h multiplied by q, where the h matrix here, which is actually contains of the row matrix, row vectors, which contain all the h values, while the q here actually contains while q here actually refers to the column vectors, and it contains all these translations and also rotation at nodes number 1, and also translation and rotation at nodes number 2. So we use potential energy approach in our lectures here to dealing with the K elements or element stiffness metric, and also to dealing with the distributed load, point load, and also the concentrated moment. So the total potential energy is given by these equations. So it contains the internal strain energy, and it also contains the potential energy. So that's why it's called as the potential energy equation, which is exactly um, the total energy that contributed from internal strain and also potential energy. So in this equation, as we look closely, this is the internal strain energy equation, and the second terms of this equation contains or dealing with the distributed loads. The third terms in this equation are dealing with concentrated loads, and the last term in this equation actually is dealing with the concentrated moments. So we can use the potential energy approach to derive the element stiffness matrix for beam element. So if we take the stiffness, if we take the internal strain energy uh, from the potential energy equation, then this is the equation that we are going to consider in developing our element stiffness matrix. So this equation actually contains a half and integrations of the E, which is modulus of elasticity. We have I, moment of inertia, and then we have the uh, double, double differentiations of dv over dx, and we square it, and then we integrate it in the x directions, where we know already that the x here equal to L over 2 multiplied by dz, which is we obtain it from this slide here. So now we need to express the square root over dx in terms of h, z, and le. So we recall that dv over dx, which is we know from the previous slide, is given by 2 over le dv over dz. So if we further differentiate this equation for one more time, then we have these expressions, and we substitute v equal to hq and simplify this equation that yields these expressions, which is given by equation number 2 in this slide. So if you work from there, then actually if you substitute this in the internal strain energy, then you will get this equation for the internal strain energy, which is, as we can see here, everything now is written in the natural coordinate system instead of in the Cartesian coordinate systems. So integrating each term in the matrix and noting that, so if we integrate from the of our element from the left to the right of z squared dz, then we get this value. If we integrate this from the left to the right of our element of this term here, then we get 0. And again, if we differentiate of dz itself from -1 until 1, then we get 2. So this internal strain energy can, as we have in the previous slide here, then if we substitute the z square here by 2 over 3, then all the z terms by 0 and the term dz, the z here by 2, then actually we can rewrite this internal strain energy in a more compact or condensed metric form as UE equal to half Q transpose. We have metric K and Q, where the K here, if you organize the equation nicely, then you can found that the K is actually contained of this 4x4 matrix. And what is contained in this K matrix is actually just the material properties of your structures. So we have this modulus of elasticity, then we have the moment of inertia, then we have the geometric informations of your elements. And this, as we can see here, this square matrix is diagonally symmetry. So this is the diagonal element, and the upper element should be the same as the lower elements, considering these this is the symmetry lines of our matrix.